Hi, welcome to a new video from Reading Research Papers series. So the paper that I am picking for today's reading is this one. It's on data efficient image transformers. I have already gone through this papers a couple of times and I have created a detailed paper dissection notes in Miro. But I'll tell you what is the significance of this paper and why I decided to dissect this paper at this point of time in the series. So one of the previous lectures that we had was on vision transformers. So the problem with vision transformer was that it was using huge dataset. So 300 million JFT dataset. It was Google's own proprietary dataset and the training took a lot of time to finish. You required a lot of GPU computational resources. So what this paper showed, the model is called DEIT. You might have seen it, DEIT model. It's called Data Efficient Image Transformer. So the title of the paper is Training Data Efficient Image Transformers and Distillation Through Attention. So the interesting thing about this paper is that it talks about few different ideas within the same paper. It's not like they introduce the idea, but the idea of teacher-student model, where how can you use a bigger pre-trained neural network for training a smaller neural network. So here the bigger neural network can be a convolutional neural network. It can be a big vision transformer. But how can you use that to train a smaller vision transformer with the help of the idea called distillation? So that is one interesting aspect about the paper. Another interesting aspect is that this paper shows that you can build on top of existing models and still be significantly efficient. So the authors of this paper show that you can simply use the ImageNet 1K dataset, the ImageNet dataset with just the 1K classes. On the other hand, the vision transformer paper, they were saying that you needed ImageNet 21K, much bigger dataset for getting sense out of vision transformer. So we will go through all these things. I'll tell you first thing which I liked about this paper personally, which was it's actually not a long paper. Although that number of pages are 22, it's not a 2-column paper. It's just a single column and there's a lot of white space. So as a researcher, I know that I should not feel like this, but as a human, when I see good famous papers that are short, I like it because I know that I can get through the paper. So when I picked up this paper for reading for the very first time, I felt happy because I knew that I will finish this paper because it was relatively short. If it had 65 pages, like for example, the clip paper has, I think 48 pages or something, I'll take much longer for finishing that paper from front to the last page. So that was my first feeling. Second thing was, while reading through the paper, I realized that I was glad that I went through the vision transformer paper first, because then I was finding it very easy to understand a lot of things that are discussed in this paper. So you will also feel the same as we go through the paper. So that was a second good thing. Third thing was just reading through it. I actually did not find it that difficult to read the paper in just one sitting. It was, although I have read it maybe 2 or 3 times, the second and third reading was just to understand it in a bit more finer detail. But I don't think it will be so much difficult for you to get through this video in just one sitting. It might be possible, but of course, as I always say, please don't be harsh on yourself. Take adequate breaks so that you will feel really good. And one more thing is, I just want to test how good my brain is working today. Like, I'm just recovering from a fever. So I first thought of recording this lecture at 6:15 a.m. As soon as I woke up. But then I thought, let me not unnecessarily push. Let me be awake. So I think I'm right now in a good mind space to just sit down and go through the paper in detail with you. And so I have written down a few points which are annotations in the paper itself. So I have added those points in the Miro board. So you will also see what my thought process was. And as always, we'll be using ChatGPT without any shame. And we will try to acknowledge if we don't know certain things, we'll try to acknowledge the fact that we don't know everything. Only then we can learn all that. And Of course, I am in a deep work mode. I lock my door and I put these sticky notes. Where is that? I just put a small sticky note outside my door saying, I'm in a deep work mode. Please do not knock. So these are small things which I do to make sure that I get some deep chunk of work done in one session. So I hope to go through the paper in one sitting, but let's see. And yeah, I mean, it's slowly becoming a habit for me. In the last few weeks, I have read more papers than I have maybe, like on an average, my weekly paper reading rate was significantly higher, much higher than what it was over the last 2 to 3 years. So I'm really personally proud of that for myself. But I also hope that through this series, you are also slowly getting into that habit of reading papers end to end, not like capsule format, like reading it end to end. So let's get into this lecture, and this time I hope you will find a lot of things easy. If you don't know about vision transformer, just I will go through the vision transformer architecture a little bit, but I still would advise you to maybe watch any vision transformer related video from YouTube. Anywhere, it can be from Visuara's channel. We have a bunch of vision transformer videos, but it can be a shorter 5-10 minute video if you don't know anything about vision transformer. In any case, I'll be discussing about it a little bit. So with that, let's get into the dissection of this paper. So this is the paper which I got from arXiv. The paper came out from Facebook AI Research. So if you search DIT paper arXiv, you will see that this is the one. So around 10,000 plus citations. So it's from a purely citation point of view, it is pretty famous, but compared to Vision Transformer, which had 75,000 citations, this may not be as comparable. But I think this paper will teach you a lot of things, even for the future, especially the distillation token, the ideas about how exactly can you perform knowledge transfer from one model to another through distillation idea. So all of these are interesting concepts. As a deep learning enthusiast, all of us should know, right? So let's go through the paper starting from the very top. So the title is Training Data Efficient Image Transformers and Distillation Through Attention. These are the authors. I don't recognize any of these names from any other projects, but I assume whenever some other papers cite using this surname Tuvron et al., we can assume that it's a DEIT paper. This is from Facebook AI Research. So let's go through the abstract. Recently, neural networks purely based on attention were shown to address image understanding tasks such as image classification. I hope they are referring to Vision Transformer paper. These high-performing vision transformers are pre-trained with hundreds of millions of images using a large infrastructure, thereby limiting their adoption. This was very much true. 300 million was their dataset size for one of the JFT datasets. In this work, we produce competitive convolution-free transformers. So that was the whole value proposition of Vision Transformer. They don't use convolution at all. So here also, you will see that in their actual architecture, there is no convolution. So they use convolution-free transformers by training on ImageNet only. And that to which ImageNet? ImageNet 1K, if I'm not wrong. We'll see that. We trained them on a single computer in less than 3 days. Our reference Vision Transformer with 86 million parameter achieve top 1 accuracy, 83.1%. So this is on the ImageNet dataset, on ImageNet with no external data. More importantly, we introduce a teacher-student strategy. So this is that important concept that I was talking about, specific to transformers. It relies on a distillation token. So this distillation token is different from the classification class token. You might remember the CLS or CLASS token, which was prepended at the starting of the Vision Transformer token sequence. So here there is a distillation token, and we'll see where it is actually appended. Is it at the beginning? Is it at the end? Does it matter? All of that we can see. Ensuring the student learns from the teacher through attention. So here, maybe based on the way of writing, we can imagine that student is probably the model that these guys are building. Teacher, we don't know what is the teacher, right? So from so far what we have read, that's what we can deduce. We show the interest of this token-based distillation. especially when using ConvNet as a teacher. So convolutional neural network is the teacher that they are using. This leads us to report results competitive with ConvNets, which is CNN, for both ImageNet, where we obtain 85.2% accuracy compared to 83.1% for Vision Transformer. And when transferring to other tasks, we share our code and models. Amazing. Very simple, straightforward, to the point, abstract. Introduction. CNNs have been the main design paradigm for image understanding tasks, as initially demonstrated on image classification tasks. One of the ingredients to their success was the availability of large training set. Of course, ImageNet dataset was considered to be large at that point, namely ImageNet. Motivated by the success of attention-based models in NLP, there has been increasing interest in architectures leveraging attention mechanisms within ConvNets. So attention was not part of CNNs until attention mechanism came into picture, and then slowly people tried to introduce attention within convolutional neural network. And then in 2019-2020 Vision Transformer paper showed that you don't even need convolution mechanism, you simply need attention. That paper title was not Attention is All You Need. That was the original 2017 attention self-attention paper, but this was 2019-2020 paper called An Image is Worth 16 by 16 Words. I hope you remember this paper. This is the Vision Transformer paper. Now it has 77K citations. 3 or 4 months ago, it had 65K. So it's rapidly growing in terms of citations. More and more people are using it. That's what it means. More recently, several researchers have proposed hybrid architecture transplanting transformer ingredients into convnets to solve vision tasks. So people use hybrid where transformer ingredients were brought into CNNs. The vision transformer introduced by Dissecting, I hope I am pronouncing the surname correctly. If not, please, excuse me, is an architecture directly inherited from NLP. So whenever now in this paper, this name Dissecting is mentioned, just assume that this is the Vision Transformer paper. Reference number 15 is an architecture directly inherited from NLP, but applied to image classification with raw image patches as input. So in Vision Transformer, images were split into patches. Patches were converted into tokens. Onto tokens, position embedding was added. And you were prepending all these tokens with if you had a token sequence, you also had a CLS token prepended. That token also had a position embedding. Their paper presented excellent results with transformers trained with a large private labeled image dataset. So this is the JFT 300 million dataset that I mentioned. It's only available for Google. It's not publicly available. The paper concluded, this is the important line, the paper concluded that transformers do not generalize well when trained on insufficient amount of data. And this is directly taken, or they are directly quoting the sentence in the paper. So this sentence, which in double quotes, is directly from the Vision Transformer paper. So basically ViT, Vision Transformer, it does not generalize well when trained on insufficient amounts of data. And the training of these models involved extensive computing resources. Again, very much true. In this paper, we train a Vision Transformer on a single 8 GPU node in 2 to 3 days, 53 hours of pre-training and optionally 20 hours of fine-tuning. That is competitive with convnets of similar number of parameters and efficiency. So basically, they are claiming that the Vision Transformer that this paper is training is fast to train, and the training time and efficiency is comparable to convolutional neural networks. It uses ImageNet as the sole training set, ImageNet 1K. We build upon visual transformer architecture from Dissecting, which is the ViT Vision Transformer paper, and improvements included in the TIM library. What is TIM library? I'm interested to see. So let's ask ChatGPT. What is TIM library? And here, maybe I can just take a screenshot and paste it here just to provide the context. The screenshot is from DEIT paper. Actually, I don't want thinking, just give me the answer. Here I'll change it to, I don't want too much thinking or anything here. Most of the questions that I'm going to ask is simple. Okay, it stands for PyTorch image models, very popular open source library that provides a huge collection of high quality pre-trained vision models. All right. So over 700 plus pre-trained models. So basically, DEIT paper references TIM. It uses standard transformer architecture from TIM to ensure reproducible comparison, easy baseline evaluation. All right. With our data efficient image transformer DEIT, we report large improvements over previous results. See figure 1. Okay, let's see figure 1. So figure 1 is this. X-axis is images per second. So this looks like the speed with which it can infer on images, how many images you can process at per second, and top 1 accuracy. Let's see the definition of top 1 accuracy. Let me take a screenshot. Then let's ask, in this figure, define what is top 1 accuracy from ImageNet. I don't have to say that, it's understood. I hope ChatGPT will know that by default. It means the percentage of test images for which the model's single most confident prediction is exactly the correct class. So basically, for what percentage of test image was the model's single most confident prediction, the exact class. So basically, its percentage score, the closer it is to 100%, the better the model. Basically, you can think of this as just accuracy for ease of understanding. So accuracy versus speed, that's what sort of this is. So a very, very good model will be somewhere here, because this is the right end of x-axis and the left, top end of the y-axis. So this means speed is high, accuracy is also high. The absolute worst models will be somewhere here. I'm sorry to see vision transformer large model here, whose accuracy will be low and efficiency will also be low. So look at where the vision transformer, this is vision transformer base model, this is vision transformer large model, more number of parameters. And these red lines are the data efficient image transformer base model with the meaning of this up arrow with 384 is fine tuning with a higher resolution image or something like that. It's mentioned in the paper. We'll come to that. This is data efficient base model with distillation. This is data efficient small model with distillation. I think they have a tiny model also, data efficient transformer TI. We'll see. Then all these yellow curves are efficient net. So efficient net is like a convolutional neural net. These blue dots are vision transformer. And this one they say hours, but I'm not sure what is this brown dots. Maybe without distillation. So this is maybe without distillation. Red is with distillation. Let's read the title. Throughput and accuracy on ImageNet of our methods compared to efficient nets trained on ImageNet 1K only. The throughput is measured as the number of images processed per second on a V100 GPU. DeiT B, which is base model, is identical to Vision Transformer B. When they say identical, I hope it's based on number of parameters. But the training is more adapted to data starving regime. It is learned in a few days on one machine. The symbol, I don't know what to call this, whatever it is called, refers to models trained with our transformer specific distillation. Yeah, so it is basically symbolizing the transformer specific distillation they are introducing in this paper. See table 5 for details. We'll come to table 5 later. Okay, so that is figure 1. Our ablation study details the hyperparameters and key ingredients for a successful training, such as repeated augmentation. So this repeated augmentation is also one interesting idea. It's not an interesting new idea. It's just that it's an interesting artifact of the way they build their model. You need to do augmentation of dataset to have a larger dataset, because you only have 21K. I mean, you have ImageNet 1K with certain number of images and you perform augmentation to create more images. We address another question, how to distill these models. First of all, what is distillation, right? We should discuss that. We introduced a token-based strategy specific to transformers and denoted by data efficient transformer DEIT with this weird symbol. I don't even know how they printed this, but whatever. That symbol and show that it advantageously replaces usual distillation. So here I had a doubt, what exactly do they mean by usual distillation? So usual distillation is something like this. I had a figure. Let me see if I can find that figure. or perhaps I can just draw here. So usual distillation looks like this. You will have a larger model with more number of parameters, which is teacher. And this will be pre-trained. Then you will have a smaller model. This is student, which is not pre-trained. So this is randomly initialized. Then you will have a data set. And this data set is primarily used for training the student. So what is done is, this is randomly initialized. This is pre-trained. Okay, and then this data is passed through the pre-trained teacher to produce a prediction. So this prediction will be based on a softmax probability distribution. Then this data is also passed through student to produce prediction. So now this is student's prediction and this is teacher's prediction. Now, what are we trying to train here? We are not trying to train teacher, we are trying to train student. So now this student, there should be some sort of loss. So loss is you compare this prediction with something, right? That is how you produce the loss. So the things that you compare, usually what do you compare this prediction against? Using the ground truth. So you will of course have a ground truth. I'll call it as GT. GT is the ground truth. Then now to construct the loss function, you consider a few things. So loss is constructed by comparing ground truth against this prediction, but also this prediction by the teacher should come into picture. So you will see how does your student's prediction compare with the teacher's prediction. And you can also have one more loss component, which is, we'll see what that looks like, but basically a KL divergence score, which takes into consideration the teacher's softmax labels. So, or teacher's soft predictions. So we'll come to that and we'll see exactly how the loss function looks like in this context. But the idea is then this loss function will be used for training or changing the weights and biases of our student model. Okay. So this is in essence how distillation usually works, knowledge distillation works, but here it is slightly different. It's mostly the same, but slightly different. It's a token based strategy. They use an extra distillation token and we'll see what that means. Okay. In summary, our work makes the following contributions. We show that neural networks that contain no convolution layer can achieve competitive results against the state of the art on ImageNet with no external data. They are learned on a single node with 4 GPUs in 3 days. Our new models, data efficient transformer, image transformer small and tiny, I think TI is tiny, have fewer parameters and can be seen as the counterpart of ResNet 50 and ResNet 18. We introduce a new distillation procedure based on distillation token. So this is the extra token that I talked about, which plays the same role as the class token, which is used in vision transformer, except that it aims at reproducing the label estimated by the teacher. So class token was trained by constructing a loss by comparing it against the ground truth in the vision transformer classification task. Here, distillation token is not directly compared against the ground truth. It is compared against the predictions made by a teacher. So that's the difference. And we'll see how to combine those two things into one single loss function. Both tokens interact in the transformer through attention. The transformer specific strategy outperforms vanilla distillation by a significant margin. Here I have put in this paper, what do they actually mean by vanilla distillation? We will see. But just remember, they have mentioned this word vanilla distillation. Here they have mentioned something like usual distillation. It's a little bit not the right choice of words in my opinion. They should maybe make it clear, but they are making it clear later. Interestingly, with our distillation, image transformers learn more from a convolutional neural network than from another transformer with comparable performance. So if we take a big vision transformer pre-trained and another convolutional neural network pre-trained, of comparable performance, the vision transformer or data efficient transformer, image transformer used in this paper, it learns better from the CNN than from the vision transformer. Interesting, right? Our models pre-trained on ImageNet are competitive when transferred to different downstream tasks such as fine-grained classification on several popular benchmarks like CIFAR 10, CIFAR 100, Oxford Flowers, all these datasets. So they have a table which shows the results from these other tasks where ImageNet pre-trained data efficient image transformer is used for further downstream tasks. This paper is organized as follows. We review the related works in section 2 and focus on transformers for image classification in section 3. In section 4, we introduce our distillation strategy, straightforward. Experimental section 5 provides analysis and comparison against both convolution neural network and recent transformer, which is basically vision transformer, as well as comparative evaluation of our transformer specific distillation. Basically, they will compare how much of an advantage they are getting because of their distillation token based approach. It includes an extensive ablation of our data efficient training choices, which gives some insight on the key ingredients involved in DEIT. We conclude in section 7. Okay. We'll see the sections anyway in detail, so no need to spend too much time on this paragraph. Related work, image classification is so core to computer vision that it is often used as a benchmark to measure progress in image understanding. Any progress usually translates to improvement in other related tasks such as detection or segmentation. So any progress in image classification also translates to progress in other tasks like detection or segmentation or tracking. Since 2012's AlexNet, ConVnets had dominated this benchmark and have become the de facto standard, no doubt about it. The evolution of the state-of-the-art on ImageNet's dataset reflects the progress with CNN network architectures and learning. They are citing a lot of papers. I am not going to look at which these papers are, but I'm pretty sure they are probably ResNet, VGG, AlexNet, and maybe EfficientNet and bunch of other convolutional neural network architectures. Despite several attempts to use transformers for image classification, until now, their performance has been inferior to that of ConVnets. So when I read this sentence, I initially got confused. Oh, are they talking about vision transformer? Because they are not inferior to ConVnet in terms of performance. Then the next sentence clarified it. Nevertheless, hybrid architectures that combine ConVnet and transformers, including the self-attention mechanism, have recently exhibited competitive results in image classification, detection, video processing, unsupervised object discovery, and unified text vision tasks. So this paragraph initially confused me because in my mind, vision transformer was indeed the state of the art just before this paper. Then this paper was talking as if transformers are not able to do things really well for images. Then I think in the next paragraph or something, they are making it clear. Recently, vision transformer closed the gap with the state of the art on ImageNet without using any convolution. So with this sentence, I was like, okay, my understanding is correct. So I was happy to see this sentence because the previous paragraph was making me feel as if vision transformer was not good. But they were not talking about vision transformer. They were talking about everything before vision transformer. This performance is remarkable since convolutional CNN methods for image classification have benefited from years of tuning and optimization. Basically, vision transformer came so quickly, so it did not have the, I would say, unfair advantage that CNN had. CNN had the unfair advantage of many years of evolution since 2012 when AlexNet happened. Then till 2020, they have evolved a lot. But still, it's amazing to see that vision transformer outperformed CNN. Nevertheless, according to this study, 15 is the vision transformer paper, which is also cited here. A pre-training phase of large volume of curated data is required for the learned transformer to be effective. In our paper, we achieve a strong performance without requiring a large training dataset, that is just ImageNet 1K. So 1K class classification. The transformer architecture introduced by Vaswani et al. So this is the attention is all you need paper for machine translation are currently the reference model for all NLP tasks. Many improvements of CNNs for image classification are inspired by transformers. For example, squeeze and excitation, selective kernel, and split attention networks exploit mechanisms akin to transformers' self-attention mechanism. So these terms are kind of new to me. So I have explained these so that I can put a screenshot to ChatGPT and briefly in one sentence explain what each of these are. In one sentence, explain each of these. I don't want to go too much into detail, but just would like to know what each of them are. Squeeze and excitation, SE blocks learn to reweight each channel of a convolution feature map by squeezing global information and exciting important channels. There was a squeeze net which had these squeezing operations. So I assume squeeze and excitation uses something similar. But anyways, let's not go into the detail. Selective kernel adaptively choose between multiple convolution kernel sizes for each spatial location, letting the model dynamically adjust its receptive field like attention. Interesting. We might have seen something or a variant of this in UNet paper. We haven't discussed the UNet paper in this series at all, but in another lecture series we had discussed about UNet. But it's not adaptive or anything. It's just, yeah, they have different convolution filters to look at more fine-grained features and more coarse features. Then split attention networks, which is RES-NEST. Split attention blocks split feature maps into groups and apply attention across them to adaptively combine channel groups, mimicking multi-head attention behavior. Okay, this sounds interesting. I think we might want to look at this paper at some point of time. But anyways, right now, let's just briefly, assume that it's okay to not fully understand these terms, and let's just move ahead, because they are anyway talking about things that were tried before. Knowledge distillation. Now, this is an important part. You should pay attention to this. Knowledge distillation, KD, introduced by Hinton et al. So this is Geoffrey Hinton, who won Nobel Prize in Physics for his work in neural networks in 2024, refers to the training paradigm in which a student model leverages soft labels coming from a stronger teacher network. So what does soft label mean? Soft label can mean something like this. So let's say you have cat versus dog classification. Let's say your model says 0.8 and 0.2 softmax probability scores. Then the model's prediction is, and let's say the first label is cat and second label is dog. Then model is essentially saying this is a cat. But that is hard labeling. If now we say that model's prediction is 1, 0, and let's say this is the teacher model, if we take that just because this cat is dominating in its final prediction, if we convert it to these hard labels, 1, 0, then we are missing out on the fact that in this particular image, the model is also thinking that 20% chance it's a dog, right? So that knowledge is missing. But these are now called soft labels, because here in this soft labels, you have the thought process of model, process of the teacher model, not just the final output. So these are soft labels. So soft label can be used for training a student model, because now if a student model's prediction is yi cap, usually you compare it against ground truth yi. But what if you compare against the soft label of the teacher? Let's say yis, t is the soft label of the teacher. Then you can construct a cross entropy loss between this, right? Minus log of something like this, minus log pi, something like minus, let's say yi student soft label from teacher sigma log yi cap, something like this. So this will look like and I equal to, in this case, it will be 1 to 2. So something like this will be the cross entropy loss, where you are not comparing against the ground truth, you're comparing against the soft labels from the teacher. We'll see this in detail in the next part of the paper when we come to the loss function. This is the output vector of the teacher's softmax function rather than just the maximum scores, which gives a hard label. There is a H missing here. So maximum scores gives a hard label like this. 1, 0 is just a hard label, but this is a soft label. It can be such a training process improves the performance of student model. Alternatively, it can be regarded as a form of compression of teacher model into a smaller one, the student. Basically, compressing whatever the teacher understood just by teaching the student what the teacher thinks for a given data point. So for a given data point, if teacher thinks that it's 80% dog and 20% cat or vice versa, you train the student to make that prediction, something like that. So you are essentially somehow indirectly compressing the teacher into a smaller student model. And what do we mean by small and big here? Simply the number of parameters. Teacher model will have less number of parameters compared to student model. On the one hand, teacher's soft labels will have a similar effect to labels smoothing. What is label smoothing? Label smoothing will look something like this. If ground truth is, let's say, 1, 0. If label smoothing parameter is epsilon, then you say that after smoothing, the labels will be 1 minus epsilon, comma epsilon. Something like this. So instead of using hard label 1, 0 as the ground truth, you use smoothened label 1 minus epsilon, comma epsilon as the smooth label smoothened ground truth. On one hand, the teacher's soft label will have similar effects to label smoothing. On the other hand, as shown by Wei et al., the teacher's supervision takes into account the effects of the data augmentation, which sometimes causes a misalignment between real label and the image. This item we need to discuss a little bit. Let's also read this one more sentence before discussing. For example, let us consider an image with a cat label that represents a large landscape with a small cat in the corner. So let's say I have a huge landscape image where cat is just here. Okay. Now in this classification, maybe just because cat is present here, this image might get classified as with the cat label, right? But you know, there are data augmentations, which is random cropping, random flipping, etc. And let's say after random cropping, you're cropping out this region. Now this crop part actually does not have cat in it. It's something else. So actually, if we use the same ground truth for uncropped image and the cropped image, it will be wrong, because in this cropped image, cat is actually not present. So that is what they are saying here. Let's read it once more. On the other hand, as shown by Wei et al., the teacher's supervision takes into account the effects of data augmentation, which sometimes causes a misalignment between real label and the image. See, here there is a misalignment between real label and the image. Real label and the, which sometimes causes a misalignment. Where is that? Misalignment between real label and the image. So here, image is actually that of a landscape only after cropping, but the label is still a cat. So the teacher might not predict cat because teacher is only seeing after augmentation, it's just seeing a landscape, right? So teacher's softened or teacher's softmax distribution may tell a different story compared to what the ground truth is, because ground truth is based on this original image before augmentation, which was cat. So that is what is saying here. So actually label smoothing and teacher's softmax labels are slightly different in principle, because in label smoothing, here what will be the case? Let's say it is a binary classification, cat versus dog versus landscape. Let's say it's a 3-class classification, not binary. Then the actual ground truth is 1, 0, 0. First one is cat, second is dog, third is landscape. After label smoothing, this will become, let's say, 1 minus 2 epsilon, 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 so that the sum will remain 1. But maybe after augmentation, although the ground truth is cat, this augmented, this cropped data set may predict something like this. Teacher may predict something like 0.1, 0.1, 0.8. So this is corresponding to cat. This is corresponding to dog. This is corresponding to some landscape. So after data augmentation, although the ground truth is this, and although the softened labels look like 1 minus 2 epsilon, 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 the teacher may actually predict something like this. So now, in principle, if you look at this, teacher's prediction and softening are not exactly the same. And why are they not exactly the same? Because of this data augmentation. What is the augmentation that we are thinking about here? Cropping. So that is what they are saying here. So technically, although label smoothing can appear similar to teacher's softmax labels, that is not exactly the case, especially for these examples of data augmentation. So for example, let's consider an image with a cat label that represents a large landscape and a small cat in the corner. If the cat is no longer on the crop of the data augmentation, it implicitly changes the label of the image. KD can transfer inductive biases in a soft way in a student model using teacher model, where they would be incorporated in a hard way. What does this mean? This sentence, KD. First of all, what is KD? I think KD is simply, here it is mentioned knowledge distillation, but there is another term called KL, KL divergence. We'll come to that. So knowledge distillation can transfer inductive biases in a soft way in the student model. So student model may or may not be a convolutional neural network. We know that convolutional neural networks have inductive biases. What are inductive biases? Locality or translational invariance. So let's look at translational invariance. There is actually a very nice GIF. Null invariance CNN. There is a very nice GIF that I have come across somewhere on, this one. So this is a translation and invariant model. If it's invariant, the logics should not change if your object is present anywhere on the image. But on the other hand, if it's translationally sensitive model, if it is not a CNN, the logics can change. That is what this animation is showing. So, and these are all inductive biases of the CNN. It assumes that whatever features present are local, and it doesn't matter where those features are present in an image. It's translationally invariant. But a vision transformer or a transformer based model, since it does not have convolution, it does not have inductive biases. But here what we are saying is knowledge distillation can actually transfer some of the inductive biases from the teacher model. Teacher model may be CNN model with inductive bias. You can transfer some of those through this knowledge distillation process. For example, it may be useful to induce biases due to convolutions in a transformer model by using a CNN teacher. This is what we just discussed. In our paper, we study the distillation of a transformer student by either a CNN or a transformer teacher. So either use CNN like ResNet or use a transformer like a big vision transformer model itself. We introduce a new distillation procedure specific to transformers and show its superiority. So that is, in my opinion, the biggest contribution from this paper, novel contribution. The distillation token. Let's see what that is. Now let's move to section 3, vision transformer overview. In this section, we briefly recall preliminaries associated with vision transformer and further discuss positional encoding and resolution. Multi-head self-attention, this we know. Attention mechanism is based on trainable associative memory. So there is key, query, and value. Query vector you have matched against key vector. So basically context vector, the final context vector matrix is equal to softmax of query times transpose of key divided by square root of D, where D is the dimensionality of the query key value space, multiplied by values. So query dot key transpose is the attention scores, divided by square root of D is the scaled attention scores. After taking softmax, you get the attention weights. And when you multiply it by V, basically you are taking attention weighted sum of value vectors. So context vector equal to attention weighted sum of value vectors. This we have discussed in detail in some of the earlier lectures. So that's the reason why there is no point in going into the architecture of multi-head self-attention right now, because that is an entirely separate course in and itself, but just wanted to give you an idea. These inner products are then scaled. So the scaling is the division by square root of D, and normalize with the softmax function to obtain k weights. The output of the attention is the weighted sum of k value vectors. Basically, attention weighted sum of value vector is the final context vector. Same equation which I wrote above. In 52, so this 52 is Ashish Vaswani, that paper, attention is all you need. A self-attention layer is proposed. Query key and value matrices are themselves computed from a sequence of n vectors. So the n vectors are input vectors. Input vectors are converted to query using WQ. So this query matrix, query weight matrix, key weight matrix will convert the input into key, value weight matrix will convert into input into value using linear transformations, meaning that attention is between all the input vectors. We know this. Finally, MSA, multi-head self-attention layer, is defined by considering H attention head. So multi-head self-attention, that is H self-attention functions applied to the input. Each head provides us a sequence of n by d, where these h sequences are rearranged into a n by dh sequence, and then it is projected to n by d. So basically, if the final dimensionality is d, and if the dimensionality in each attention head is h, then basically, or dimensionality in each attention head is small d, and you have h number of such heads, d is equal to d multiplied by h. You have h heads, each head is taking care of dimensionality d, so that the final dimensionality of the context vector coming out of your multi-head self-attention will be product of these two. And in many models, the final dimensionality d is same as the input token's dimensionality, the dimensionality of this x input token. All right, so this, I know I'm going a little bit fast in this section because it's not my intention to teach you multi-head self-attention in this lecture. I have covered that in detail in some of the earlier lectures, but here it's just to go through the paper. Now, transformer block for images. Transformer block for images. To get a full transformer block as in 52, which is attention is all you need paper, we add a feed forward network on top of multi-head self-attention. The feed forward network is composed of two layers with JLU activation. So in the hidden layer, basically you project your dimensionality from D to 4D. So you project into a higher dimensional space in the hope of making the context vector embeddings much more richer. And then you project it back from 4x higher space into the original dimensionality. Both multi-head self-attention and feed-forward neural network are operating as residual operations thanks to skip connections. So there are skip connections going around each of these with layer normalization. So this is the standard transformer block architecture, which was used exactly the same as in attention is all you need paper. In order to get a transformer to process images, our work builds upon the vision transformer model from the vision transformer paper. It's a simple and elegant architecture that processes input images as if they were sequence of input tokens. So the fixed size input RGB is decomposed into batch of n patches. The size of each patch is fixed to be 16 by 16 pixels, and the total number of patches per image will depend on the image resolution. Each patch is projected into a dimensional space of 768 dimensions, and a linear layer is used for this. The transformer block described above is invariant to the order of the patch embeddings and thus does not consider their relative positions. So the transformer block is, it doesn't matter the ordering of the patch position, whether you keep one patch as position number 1 and another patch at position number 3, etc. So the vanilla conversion of patches into tokens is not enough, which is why you add positional embedding on top of it. The positional information is incorporated as fixed or trainable position embeddings. So in vision transformer paper, they have tried both fixed embeddings as well as trainable embeddings for position embedding, and both were found to be working kind of similar to each other. They are added before the first transformer block to the patch tokens, which are then fed into the stack of transformer blocks. So this first paragraph was about transformer. This is about vision transformer. And next is about class token within the vision transformer. The class token is a trainable vector appended to the patch of tokens before the first layer that goes into the transformer layers. So an image which shows this will be worth it. You can simply search vision transformer paper and then open this. The figure number 1 or 2 describes the architecture. Figure number 1 itself. So here, this token number 0 is the class token, and 0, 1, 2, 3, those are position embeddings. This pink color items, these are the actual input token embeddings. To that, you are adding the positional embedding. So the position embedding is also 768 dimensional vector. So it's appended. In the original transformer paper, they use the word prepended. Basically the same. You are appending at position number 0, or you are prepending to an existing sequence. And then it is projected with a linear layer to predict the class. So what is this projection? Multi-layer perceptron head, MLP head. So only the class token, the context vector corresponding to the class token only goes into MLP head. So although here there are 10 tokens, the 10 tokens are used for creating the attention weights, and then attention weights are used for converting the input class token into final context vector class token. And that is what goes into the MLP head, and then MLP head will project it into a classification space. So if there are 10 classes that you want to classify it to, you will be projecting it into a 10-dimensional space. So it is then projected with a linear layer to predict the class. The class token is inherited from NLP, specifically from BERT paper. I don't know which is this 14th paper. Maybe it might be BERT paper. Let me go to the references section and see whether it's the BERT paper or not. Actually, don't worry by seeing so many pages. There are many pages are big tables, and we will get through it relatively fast. Yes, so 14th paper is BERT paper by Devlin BERT, pre-training of bidirectional transformers for language understanding. So BERT paper introduced this CLS token for doing classification tasks. All right. The transformer thus processes batches of n plus 1 tokens. Why? N because there are n patches in each image, plus 1 because you have now position embedding for the, or you have the classification token also. N plus 1 tokens of dimension d, of which only the class vector is used to predict the output. So only the context vector corresponding to class token is used for predicting the output. This architecture forces the self-attention to spread information between patch tokens and the class tokens. So the multi-head self-attention architecture forces the self-attention to spread whatever information is there in the patch token and class token. Although in the architecture that they use here, the patch tokens can go from 1 to n, and class token is at the 0th position. So although the last nth token and 0th token, they are far apart, you can have mixing of information between those two because attention mechanism allows for long range dependency. At training time, the supervision signal only comes from class embedding, while the patch tokens are the model's only variable input. So the patch tokens are these are the 9 patches, and these are the 9 patch tokens, 1 2 3 4 5 6 7 8 9. But then the signal for training only comes from class token. Why? Because only class token is going outside here. Class token's context vector goes into MLP head. So whatever loss function we construct, that loss is coming because the class token is not doing the right thing, right? And then that is propagated into the weights in the transformer encoder. But input comes from all the patches. Input is coming from these 9 patches. Output is going out in the form of class token. That is the 5th page. Now let's go to the next page. Fixing the positional embedding across resolutions. So Tuvron et al. Show that it is desirable to use a lower training resolution and fine-tune the network at a larger resolution. In fact, Vision Transformer paper also had done the same thing. So for the first several epochs, they used lower resolution training to make the training process fast. It's mentioned somewhere in their supplementary, lower resolution or low resolution. Let me go to the last section of the paper. Maybe I think it's somewhere here. Yes, it is often beneficial to fine-tune at a higher resolution than pre-training, but that is about fine-tuning versus pre-training. But I'm talking about within pre-training itself. I thought they had a resolution adjustment. Maybe I'm wrong. Maybe I'm just remembering it in a wrong way. And running fine tuning at it. So I know that fine tuning is done at a different resolution. That is not what I'm thinking. I thought within the training they had, for the first several number of epochs, they had a lower resolution, and for the later epochs they had a higher resolution. Anyways, I cannot find it by just searching this resolution keyword, but doesn't matter. We can figure it out later. But here what you're saying is training at a lower resolution and fine tuning at a higher resolution. This speeds up the full training and improves accuracy under prevailing data augmentation schemes. When increasing the resolution of an input image, we keep the patch size the same, and therefore the number n of input patches does not change. So what is said is, when increasing the resolution of an input image, we keep the patch size the same. Therefore, the number of n input patches does change. I was getting confused because I read it as does not change, but it does change, because if input image is having W as the width and H as the height, and let's say patch size is P, total number of patches along the width is W by P, total number of patches along the height is H by P. Obviously, so this is basically W H by P, and if W and H I call as image size I, then basically I square by P square. Total number of patches I have per image is I square by P square. So obviously, if image resolution I changes, number of patches are going to change. So that is what they have mentioned here, but I read it as it does not change. It actually says it does change. Makes sense, obviously. When increasing the resolution of an input image, we keep the patch size same. Therefore, the number of input patches does change. Due to the architecture of transformer blocks and the class token, the model architecture do not need to be modified to process more tokens. So basically what we are saying is the position embedding was a learned token. Now let's say you have 10 patches in your input image. You'll have 10 plus 1, 11 positions whose position embedding need to be learned. Now, what if you increase the image resolution? Total number of patches may go from 10 to 15, let's say. So you now have 15 plus 1, 16 positions for which you need the position embeddings. But then are you now going to train again? No. What they do is, in contrast, one needs to adapt the positional embeddings, because there are n of them, one for each patch. So if number of patches increase, number of position embedding vectors also increase. But Dosovitsky et al., which is the vision transformer paper, interpolate the position embedding when changing the resolution and demonstrate that this method works with the subsequent fine-tuning. So in the fine-tuning stage, you don't need to have new learned position embedding vectors. You can interpolate with the existing position embedding vectors to create more position embedding vectors for more positions. So that is what was done in the original vision transformer paper. Same will be done here. Now comes the interesting part: student-teacher model, or distillation, knowledge distillation, KD. Distillation through attention. In this section, we assume we have access to a strong image classifier as a teacher model. So the strong image classifier can be CNN, it can be a big vision transformer. It could be a ConNet or a mixture of classifiers. We address the question of how to learn a transformer by exploiting this teacher. So if we had a pre-trained teacher model, how can we make it useful for teaching a transformer? As we will see in section 5, by comparing the trade-off between accuracy and image throughput, it can be beneficial to replace a CNN by a transformer. Why do I say that, or why does the paper say this? Just go to figure 1. In figure 1, in fact, it is beneficial to replace CNN with a transformer, because these three are transformer architectures, data efficient image transformer. And look at its performance compared to our traditional CNN. These are all efficient net, different convolutional neural networks belonging to the variant efficient net. And you can see that the speed of processing and the accuracy are both higher. The data efficient transformers are in general lying in the right top quadrant of this graph. So yes, of course, it is beneficial to train, but we will see what exactly is done. As we'll see, it can be beneficial to replace CNN with a transformer. This section covers two axes of distillation: hard distillation versus soft distillation, and classical distillation versus the distillation token. Let's see what this idea is. Soft distillation. It minimizes KL divergence, Kullback-Leibler divergence. I don't know if this is the exact pronunciation, but we'll call it as KL divergence between the softmax of the teacher and the softmax of the student. So now let's read this, although I know that this equation might look a bit intimidating at first. I promise you that it's not. It's actually easy. Let ZT be the logits of the teacher model and ZS the logits of the student model. What are logits? Logits are the inputs that go into softmax. Logits are numbers that need not look like a probability distribution, but it can be used for creating the probability distribution after passing through softmax. We denote by tau the temperature for the distillation and lambda the coefficient balancing KL divergence loss and cross entropy loss. So now let's look at these terms. So this is the cross entropy loss, LCE, loss due to cross entropy. And in the cross entropy loss, you are first taking softmax of your logits from the student. So student's output. So student is the smaller model. students' output logits are passed through softmax to get the probability distribution of the predictions. And these predictions are compared against the ground truth. Ground truth is y. And how how is this comparison done? It is done using cross entropy loss minus yi log pi and summation of that minus sigma yi log pi. Let me write it over here. Minus sigma yi log pi, where pi is the prediction, yi is the ground truth, and this is done over all the classes in the prediction. And 1 minus lambda, because lambda is the factor that balances how much fraction of this final loss should be contributed by the cross entropy loss due to the student not being able to predict close to ground truth, and how much should come from the teacher. Now this is due to student and this is due to teacher. Teacher is multiplied by lambda, students whatever is there multiplied by 1 minus lambda. So usually the value can be 0.5. So half of the contribution comes from the error due to student, half comes due to the error due to teacher. Now what do we mean by error due to teacher? So in teacher, what we have is two types of logits. The first set of logits is student due to logits due to student. Second set of logits are logits due to teacher. So ZS is logits coming from student, ZT is logits coming from teacher. You are dividing this by a temperature term tau so that you can make the softmax a little bit more sharp or blunt depending on the value of tau. If value of tau is greater than 1, softmax will become a little bit more blunt. It will not be, whichever are the higher values of softmax, they will become a little bit more smaller if tau is greater than 1. If tau is less than 1, you amplify the softmax sharpness. So that is temperature. For now, just imagine tau value is 1. Tau equal to temperature equal to 1. So you first get softmax probability distribution corresponding to logits of teacher. Then you need softmax probability distribution due to logits of, so first one is student, second one is teacher. And then this KL divergence score is an interesting formula. Instead of writing it, I will make ChatGPT display the formula. First, let me just clean this up. So this is the KL divergence. Give me the loss formula here. So first one will be summation of a negative logarithm. Second one is also a logarithm, but there is a fraction. Negative logarithm of softmax probability of ratio of teacher to student. But let's look at the formula here. Yes, I want to break down. I want the KL formula, KL divergence formula. So KL divergence formula is this: sigma I pi log pi by qi. So in this context, it will be pi is the softmax probability distribution, ith item. Qi is the softmax probability distribution, ith item. So if we had, let's say, 3 items here, let's say my logits Z of student is 0.1, 0.1, 0.5. Then I can have probability due to student by taking softmax of this. So sigma of ZS, and let's say it looks something like last item is 0.9, this is 0.05, this is 0.05. I know that softmax of these 3 numbers will not result in this, but I'm too lazy to do the calculation right now. Let's say now similarly for teacher, these are my logits, 0.5, 0.1, 0.1. Which means the probability due to probability distribution for teacher will be softmax of ZT, logits for teacher, and let's say it is 0.9, 0.05, 0.05. Now the KL divergence is calculated between these two set of numbers. So the formula is what is shown in the paper itself. Let me just write it down. T square multiplied by or tau square, this is not T, at T or tau for temperature, KL divergence between PS and PT. I think instead of PS and PT, they might have written it as tau square multiplied by KL divergence of softmax of ZS, which is logits for student, and softmax of ZT, where ZT is the logits for teacher. I think this is how they have written it, right? Oh yeah, they also have a temperature term. So while calculating softmax, you are dividing this by the temperature term. The same temperature term is taken as a square outside here. But now the question is, what is this KL divergence formula? How does it look like if you have PS and PT? So it will look like what is shown here. Softmax due to student multiplied by softmax due to student by softmax due to teacher. So let's write it here. So negative, I don't think there is negative sign here. They have written it without negative sign. So sigma I P due to teacher I, right? Not due to student. Actually, it is student. Probability ith probability item for student multiplied by log P SI divided by P TI. Now this I will run from how many other items are there? There are 3 items, right? Here we are looking at 3 classes. Now what if my PS and PI were exactly the same? In this case, they are not exactly the same. PS is 0.05, 0.05, 0.9. Here it is 0.9, 0.05, 0.05. But assume that they were exactly the same. If my teacher and student are making the exact same predictions, then I should not have any loss contribution due to that. Because I am trying to teach the student to make the exact same predictions of the teacher, and student is doing that. So if student's predictions were also 0.9, 0.05, 0.05, then the error loss should be 0. And how is that 0? Because PSI and PTI will be the same, which means logarithm of something by something, where it is 1. So logarithm of 1 is 0. So the contribution due to every single term for the loss will be 0. But let's say I have teacher probability like 0.8, 0.1, 0.1. Okay. This is the probability distribution from teacher. Let's call it as PT. And let's say my student is saying something like 0.8. This is fine, but this is 0 and this is 0.2. In this case, look at this. Student is with great confidence. Student is saying that the item is not second class 2. Whatever the current item you are looking at is definitely not the item with label, second label. So this is the first label item. So let's say it is cat, dog versus something else. So first item, let's say it is cat. Second is, let's say, dog. Third is background, BG. So now what student is saying this is, student is 100% certain that this is not dog. But teacher is not 100% certain. Teacher is still assigning 10% probability for this to be dog. So for this overconfidence that student is having, there should be extreme penalty. And look at it, how this extreme penalty comes. So now the KL divergence will be calculated in the following way. 0.8 multiplied by, so PSI, the student's first item, I equal to 1, 0.8 multiplied by logarithm of 0.8 by 0.8, which is 1. So logarithm of 1 is 0. So this whole item will become 0 plus 0.1, actually student, right? 0 multiplied by PSI divided by PTI. I also noticed that there is a small error in this formula. Actually, here we are forcing the student to learn teacher, not vice versa. We are not forcing the teacher to learn from the student. So here the S and T should be flipped. So the actual formula should be, this should be the probability ith for the ith item for teacher. And this should be PTI. and this should be PSI. So this 0.8 multiplied by log, this one is correct. Next should be 0.1 multiplied by logarithm of 0.1 by 0 plus 0.1 multiplied by logarithm of 0.1 by 0.2. So this 0.1 is this 0.1 is this for teacher, PT. So now you see this value is now going to blow up because logarithm of a huge number is a huge number. So, and why is this big error coming? And this is an extreme case, right? No model is going to predict exactly 0. This will be a very small number, but you are penalizing the model for making such a confident prediction. This is a confident prediction. When a model says 1 or 0, it's a confident prediction. So you are penalizing the model for that, because although teacher thinks this is 80% is a cat, teacher is still assigning 10% likelihood for the image to be dog. Student is not doing that, and that's the wrong thing. That's why we are penalizing it heavily. So this is how the KL divergence look like. And one additional thing is you are multiplying the KL divergence score by T square. Let's ask ChatGPT why this T square multiplication is there. Why is there a multiplication by T square for the KL divergence score? It must be because we are normalizing, we are dividing by temperature in the softmax score, but let's see the reason. It's not arbitrary. It's mathematically necessary to keep gradient magnitude consistent when using temperature greater than 1. Why do you multiply it by T square? Because increasing the temperature softens the softmax, makes sense, which makes the gradient shrink by a factor of 1 by T square. So basically, when you divide inside the softmax by T, gradient of that softmax term will shrink by a factor of 1 by T square or 1 by tau square. So to normalize this, you are multiplying by tau square. So that is the reason why this tau square term exists. Because you are taking dou loss by dou weights, right, for gradient descent. So when you take the dou loss by dou weight, when there is a 1 by tau term inside the softmax, it will introduce an extra 1 by tau square term in the loss, and to cancel that you are multiplying by T square. So that is why T square exists. Lambda exists because you are taking weighted sum. So 1 by lambda is 1 minus lambda will be 1 minus 0.5. So if lambda is 0.5, both these terms will equally play. 50% of the global loss will come due to cross entropy loss. 50% will come due to KL divergence. Otherwise, depending on the value of lambda. So this is soft distillation because we are not taking the actual predictions made by the teacher. Rather, we are taking the softmax distributions of the teacher. We did not say that teacher is thinking this to be a cat. We did not say that. We said teacher is thinking this is 80% a cat. Teacher is thinking it's 10% dog and 10% background. And when the student is thinking it's 80% cat, 0% is dog and 2% it's 20% it's background, that's an issue. That's when we saw the example where loss is blown up. Okay, now let's come to hard distillation. So hard label distillation is we introduce a variant of distillation where we take hard decision of the teacher as the true label. So hard decision meaning whatever is the prediction. So here, what is the hard label? Hard label corresponding to teacher will look like something like 100, or the fact that the label is corresponding to that of a cat, simply because this is the item with the highest value. So that will be like a hard label. So if we say that the hard label is compared against the softmax score, so in one case for student, in one loss term due to cross entropy, you are comparing the cross entropy loss between predictions made by the student and actual ground truth. Here you are constructing another cross entropy loss term where this is the predictions made by the student and this is not the actual ground truth. Here you are saying whatever teacher says as the highest number, that is the ground truth. So if teacher thinks 80% this is a cat, then I will say that ground truth is cat for this particular term. And then 50-50. So half of the contribution to the final hard distillation global loss come from the actual ground truth term, and remaining half of the loss will come due to the teacher-based ground truth. For a given image, the hard label associated with the teacher may change depending on specific data augmentation. As you saw, the hard label, if there is a cat somewhere in the corner, if we crop the image, the hard label due to teacher may change from cat to background. we will see that this choice is better than the traditional one while being parameter free and conceptually simpler. So this is conceptually simpler than this, because here you have to take KL divergence here and more parameters, and here it's not there. The teacher prediction YT also plays the same role as the true label Y. Both are the same cross entropy loss formula. Note that the hard labels can also be converted into soft labels by label smoothing. What do we mean by that? Label smoothing. We'll say teacher thinks this is a cat. So these are now hard labels. But if we want to do label smoothing, we'll say define a term called epsilon. And then we say this is 1 minus 2 epsilon. This is epsilon and this is epsilon. Maybe epsilon can be 10 raised to minus 3. Then this will be 1 minus 2 into 10 raised to minus 3, the first term. Second term will be 10 raised to minus 3. Third will be 10 raised to minus 3. So you are assigning non-zero probabilities to other items also. You can do that. So that will be like label smoothing. Label smoothing is very different from soft distillation. Okay, so don't confuse between soft distillation and label smoothing. Very different things. Where the true label is considered to have a probability of 1 minus epsilon, and remaining epsilon is shared across the remaining classes. So in that case, true label can be 1 minus epsilon. Other terms can be epsilon by 2, epsilon by 2. Or one of them can be epsilon by 3. This can be 2 epsilon by 3. In either case, sum of all these three should be 1. We fix this parameter epsilon equal to 0.1 in all our experiments that use true labels. Okay. So in soft distillation, in hard distillation, if they are using label smoothing, they keep the value of epsilon to be 0.1. Now, this is the architecture diagram that they have. In my opinion, this is not the best possible diagram. They could have shown a better diagram. Let me show you one diagram which I had created myself. So this is a diagram which I had made to replicate data efficient image transformer. It's a GIF. So let me see if this can play. Yeah. So let's just follow these flowing arrows. So input image is converted into patches. Patches are converted into sequence of patches. So these are now sequence of patches. And to this sequence, we prepend a class token. And finally, at the end, we append a distill token. Now, for each of these tokens, you have input embedding, which are directly converted, patches converted to vectors or random vectors corresponding to class token and distill token, to which you are adding position embedding. Position embedding will depend on the position. Class token will have position 0. This will have position n plus 1. So totally there will be n plus 2 tokens. So final token embedding is the sum of input embedding and position embedding. Then it passes through transformer blocks. When I say transformer blocks, it includes everything. It includes transformer blocks with layer normalization. Inside that, it will have linear projection like the multi-layer perceptron, right? And then finally, class tokens context vector will come here. And this is the classification head corresponding to classification token. And this is the distillation tokens classification head. And then distillation token will make bunch of predictions. Class token will make bunch of predictions. At the same time, the input image will be passed through a teacher. So now this whole thing, I will erase this. I'm sorry for drawing it in such a not so beautiful way. But this whole thing is the student. And this pre-trained CNN or pre-trained vision transformer, it can also be vision transformer, but here I'm saying it's a CNN. It is the student. Now let me just delete all of these annotations. Now teacher, what will the teacher do? So for the same input, teacher will make a prediction. Let's call this as Y teacher cap. Class token will have a prediction. Let's call it as Y class cap. This is student, by the way, and this is Y distillation token cap. And there is ground truth. Ground truth we call as Y. Now we can construct a loss where we compare the predictions made by class with the actual ground truth. And we compare the predictions made by CNN, which is the teacher, with the predictions of the distillation. So these two we compare, and these two we compare, and we add those two together to produce the loss. And this loss is not used for training the teacher because teacher is pre-trained. This loss is used for training the student. This vision transformer model. Right? That is what is done. So this diagram shows exactly that. You have multiple attention heads. So these are multiple transformer blocks. So these are bunch of transformer blocks which contain self-attention and feed forward neural network. So self-attention followed by feed-forward neural network. Inside there is layer normalization. There is also residuals. And first token or zero token is class token. Last token is distillation token. Zero tokens representation is used for constructing cross entropy loss, where this is compared with Y. Teacher is compared with predictions made by the, distillation token is compared with predictions made by the teacher, Y, T, cap. Here, Y, T, cap. So Y made by the class token, Y cap made by the class token is compared with Y, where Y is the actual ground truth. And Y cap made by distillation token is compared with Y cap made by the teacher. Okay, so this is how the total loss is constructed. Now let us read this figure 2. Although they are yet to reference figure 2, our distillation procedure, we simply include a new distillation token. It interacts with the class and patch tokens through the self-attention layers. Distillation token is employed in a similar fashion as that of class token, except that on output of the network, its objective is to reproduce the hard label predicted by the teacher. So this paper saw that hard distillation is better than soft distillation. So here, this will try to predict the hard label. Maybe there is labels of smoothening. Maybe that is there, but it's hard distillation. It's not soft distillation. Predicted by the teacher instead of true label. Both the class and distillation tokens input to the transformers are learned by back propagation. So one confusion that I had when I was initially learning about data efficient image transformer was, is the distillation token initialized by the CNN itself? Because then you are having CNN in the pipeline. But that is not the case. Distillation token is initialized as randomly as the class token. The only thing which distillation token influences is the final context vector corresponding to distillation token is compared with whatever the output is produced corresponding to input image by the teacher. So teacher is only coming to guide the distillation token, this value, this loss function. Teacher is not coming to influence directly the value of distillation token. Teacher indirectly affects the value of this whole network by providing a guide to what the distillation tokens context vector should be. Distillation tokens context vector ideally should be exactly same as the hard labels of the teacher. So that is the only thing that teacher is doing here. Teacher is not directly influencing the distillation tokens value. Teacher is not directly providing the value or anything here, but teacher is providing the ground truth for the distillation tokens context vector. Now, distillation token. We now focus on our proposal, which is illustrated in figure 2. We add a new token, the distillation token, to the initial embeddings, which is patches and class token. Our distillation token is used similarly as the class token. It interacts with other embeddings through self-attention and is output by the network after the last layer. Okay, let's read this. Our distillation token is used similarly as the class token. It interacts with other embeddings through self-attention. What do we mean by other embeddings? Other embeddings means there are other patches. There are n plus 2 patches, n for the images, one for class token, one for distillation token. They all interact with each other through self-attention and output, and distillation token is output by the network after the first layer. Its target objective is given by the distillation component of the loss. So the loss has two components. One is the loss due to class token. One is the loss due to distillation token. The distillation embedding allows our model to learn from the output of the teacher as in a regular distillation while remaining complementary to the class embedding. So what do we mean by while remaining complementary to class embedding? The teacher here is making a prediction on your input image, and distillation token, just like in regular teacher student model, it will try to mimic teacher's prediction. It will try to make same predictions as that of the teacher. And class token is doing something similar, except class token is not trying to mimic the teacher. Class token is trying to mimic ground truth, right? So that's the only thing. Interestingly, we observed that the learned class and distillation token converge towards different vectors. This is interesting, right? Interesting, but it's also a little bit obvious because see, distillation token is anyways, we are not trying to match the distillation token's value to ground truth. That is not what's happening. Distillation token's value is, we are trying to match it to the predictions made by the teacher. Similarly, class token, its value, we are not trying to match with the teacher. We are trying to match the class token's value with that of the ground truth. So obviously, teacher might not be making all predictions correct in the ground truth, right? Teacher knows some things, but teacher will have teacher's own mistakes, right? So whatever teacher has learned is completely, or it's not exactly same as ground truth. And because of that, the distillation token and class token will not look exactly the same even after training. The cosine similarity between them will not be exactly equal to 1. So that is what is written in the paragraph. The average cosine similarity between these tokens equal to 0.06. So here when they say average, I did not fully understand average across different layers. Is that what they're saying? Let's ask. So then let me say this screenshot is from the DEIT paper. What does it mean by average cosine similarity here? Because if it is averaged through different transformer blocks, it doesn't make, I can't believe that it's so small. The cosine similarity is so small. How similar the class token and distillation token when averaged across many images or across the dataset. Okay, makes sense. Okay. So you look at the value of distillation token and value of class token for one image. You do that for another image, then for another image. So like that, you compare the value of distillation token and class token for many different images and see how much is the average cosine similarity. The average cosine similarity is actually only 0.06. So clearly, distillation token and class token are seeing different things. As the class and distillation embeddings are computed at each layer, they gradually become more similar through the network all the way through the last layer at which similarity is high, cosine similarity equal to 0.93. So let me see what ChatGPT has to say about that. Okay, this is average cosine similarity. That is fine. The class token learns to predict actual ground truth. Distillation token learns to mimic teacher's distribution. We know that. Because both tasks are related, the tokens gradually move closer in representation space. But since they serve slightly different objective, they fully do not collapse. So early layer, okay. So maybe this 0.06, they are talking about early layers, early transformer block layers, like early layer meaning this layer. So in this layer, maybe for a bunch of images, the similarity between distillation token and class token is only 0.06 cosine similarity. By the time you reach here, it becomes 0.93. What becomes 0.93? The average cosine similarity between distillation token and class token over many different images. That becomes 0.93. If this is my current understanding, I am not 100% sure if that is exactly what is mentioned here. Like they did not explicitly say whether this 0.06 is in the earlier layer or not. But I hope that is what they are saying. But still the cosine similarity is less than 1. This is expected since they are aimed at producing targets that are similar but not identical. What does it mean similar but not identical? Not identical because target of class token is the ground truth. Target of distillation token is teacher's prediction. So they are similar but they are not identical. But they say one more thing in the paper. Pay very close attention to this next paragraph. We verified that our distillation token adds something to the model compared to simply adding an additional class token associated with the same target label. So what if we had two class tokens, one class token at the 0th position, another class token at the n+1th position, and both class tokens were forced to learn the actual ground truth rather than the, let's say, ground truth and teacher's prediction. Then even if we initialize these as random, they converge towards the same vector 0.999 cosine similarity. So the introduction of distillation token is very different from introduction of just another class token. If we simply added another class token where that also is now forced to learn just the actual ground truth, then those two tokens are no different. They are both going to learn the same thing. But here, one token is learning the actual ground truth, another token is learning from the teacher. So that difference is actually important. This additional class token does not bring anything to classification performance. In contrast, our distillation strategy provides a significant improvement over a vanilla distillation baseline as validated by our experiments in section 5. We'll see when it comes to section 5, which is the next section. Fine-tuning with distillation. We use both the true label and teacher prediction during the fine-tuning stage at higher resolution. So higher resolution meaning fine-tuning is done using higher resolution images. We use the teacher with the same target resolution, typically obtained from the lower resolution teacher by the method of Tuvron et al. So teacher is originally method typically obtained from the lower resolution teacher. We use a teacher with the same target resolution, typically obtained from the lower resolution teacher by, okay, so I guess if I understand this correctly, they fine-tune the teacher also with a high resolution image. Is that what this means? Let me ask GPT. Here, what do they mean by low resolution teacher? Are they fine-tuning teacher also with a high resolution data set? Because usually in student teacher model, teacher is untouched. But here I'm not sure whether that's what the paper is saying. Great question. This is in line. What does low resolution teacher refer to? Teacher model is usually a ConvNet originally trained on 224 by 224 AI. Student fine-tuning resolution is 384 by 384 or even this much. Thus, the teacher is a low resolution teacher because logics come from images that are of small size. However, when we fine-tune the student at a higher resolution, they need the teacher also to output predictions at that resolution. But the teacher was only trained at 224 by 224. So how do they obtain teacher at 384 by 384? They don't retrain from scratch. Instead, they apply resolution adjustment trick. Okay, so teacher is adapted to higher resolution using a very small amount of fine tuning, few epochs, not full training. Okay, fine. That's all I wanted to know. I just wanted to know if teacher, little bit of fine tuning is done on the teacher or not. That is what is done. We have also tested with true labels only, but this reduces the benefit of teacher and leads to lower performance. We will see. I hope they will show this in a table. Classification with our approach, joint classifiers. At the test time, both the class or the distillation embeddings produced by the transformer are associated with linear classifiers and able to infer the image label. Yet our referent method is the late fusion of these two separate heads, for which we add the softmax output by two classifiers to make the prediction. So this is, in this what they're saying is, for once you have the, trained student, which output from the student will you take to get your final prediction? Will you take the output from class token or will you take output from distill token? That's the question, right? So here they are coming up with a joint classifier. We will see what that is in section 5, but just keep this in mind. Keep this question in your mind. Once the student is trained, will you use the representation from class token or will you use the one from distill token? Which one are you going to use? Are you going to use both or are you going to use only one of them for your final predictions? Let's see at the testing time. So now we come to the 5th section. So we are almost, very close to wrapping up the paper because the paper has only 7 sections. Experiment section is a lot of experimental details and big tables. So we'll go through this very easily. But I think you already understand a good section of what the model architecture is about. Now let us move to section 5, experiment section. This section presents a few analytical experiments and results. We first discuss our distillation strategy, then we comparatively analyze the efficiency and accuracy of convnets and vision transformers. Okay, 5.1 transformer models. As we mentioned earlier, our architecture design is identical to that of the vision transformer paper. There is no convolution, and our only differences are the training strategies and the distillation token. Also, we do not use MLP head for the pre-training, but only a linear classifier. So what that means is MLP classification head, which was present in the vision transformer paper. Instead of that, they're saying they use a linear head. So I was a little bit confused because I did not remember entirely whether the MLP head contained a hidden layer or not. Because if it contained a hidden layer of 4x higher dimension, so let's say if it is a 768 dimensional context vector, you project it into a 4x dimensional space and then you project it back into, let's say, same dimensionality and then perform classification. Something like that. So let's ask ChatGPT whether this means vision transformer does not contain a hidden layer, whether that's what this means or not. So in vision transformer MLP classification head, is there a hidden layer? So they mentioned two differences. One is in the pre-training, another is in the presence of distillation token, and third is they say their MLP head is slightly different. They use only a linear classifier. So that is what we are checking now. Yes, in the original vision transformer, the classification head includes an MLP with a hidden layer. Data efficient image transformer removes the hidden layer and it just uses a linear classifier. Okay, fine. And the hidden layer dimension was, what was the, in ViT, what was the dimension of the hidden layer in MLP classification head? I think it was 4 times whatever was the input dimension, but I might be wrong. Okay, layer equal to 4 times the hidden dimension. Okay, fine. All right, makes sense. So they don't have that hidden layer, that's all. So you directly go from, let's say, 768 dimensional projection to whatever is the number of classes. If your classes are 1000 class classification, the final layer will have 1000 nodes. To avoid any confusion, we refer to the results obtained in the prior work by ViT. So ViT means it will be the previous vision transformer, and prefix ours by DEIT. If not specified, DEIT refers to our base model, which has the same architecture as vision transformer base. When we fine-tune the data efficient image transformer at larger resolution, we append the resulting operation by this thing, up arrow with 384, because fine-tuning is done with 384 by 384 images. Pre-training was done using 224 by 224 size images. Last, when using our distillation procedure, we identified with a alembic sign, whatever this is pronounced as, DEIT with this alembic sign. The parameters of vision transformer B and therefore data efficient transformer B, image transformer B, are fixed as D equal to 768, number of attention heads are 12, then dimensionality inside each attention head is 64. We introduced two smaller models, DEIT-S for small and TI for tiny, I think, for which we changed the number of heads, keeping the D fixed. So D is fixed, so 64 is fixed, but number of heads might be 6, which means hidden dimension will be 64 multiplied by 6. Table 1 summarizes the models that we consider. Okay, let's see where is table 1. This is table 1, variants of our DEIT architecture, tiny, small, and base model. So total number of parameters in tiny is 5 million, the other is 22 million, last one is 86 million. This base model is comparable to the transformer architecture in vision transformer paper, which had around 84 million or something like that parameters. The larger model DEIT-B had the same architecture as that of vision transformer B. The only parameters that vary are the embedding dimension and the number of heads. And we keep the dimensions per head constant, which is equal to 64. All right, this is fine. Table 2 we compare. We are yet to come to table 2 in the text. So let's first read the text. Distillation. Our distillation method produces a vision transformer that becomes on par with the best conv-nets in terms of trade-off between accuracy and throughput. See table 5. Table 5 we don't see yet. It's later in the paper, but in figure 1 we had seen that accuracy on the y-axis and throughput on the x-axis. Interestingly, the distill model outperforms its teacher. Amazing, right? So the distill vision transformer outperforms the teacher ResNet or whichever model they are using in terms of the trade-off between accuracy and throughput. Our best model on ImageNet 1K is 85.2% top 1 accuracy, outperforms the best vision transformer base model, which was pre-trained on 300 million dataset that had only a accuracy of 84.15. So more than 1 percentage point improvement. It's really amazing in deep learning, in computer vision. For reference, the current state-of-the-art 88.55 achieved with extra training data was obtained by the Vision Transformer H huge model with 600 million parameters. So state-of-the-art at this point is 88.55%, but compared to this 86 million parameter model, that is 600 million parameters trained on JFT 300 million dataset, that too at resolution 512. Here training is done at 224 by 224 resolution on 86 million parameters and on ImageNet 1K dataset. Hereafter, we provide several analysis and observations. ConvNet teachers. We have observed that using a coordinate teacher gives better performance than using a transformer. This we discussed earlier, but results we are yet to see. Table 2 compares distillation results with different teacher architectures. The fact that coordinate is better teacher is probably due to the inductive bias inherited by the transformer through distillation. So if the teacher is coordinate versus another bigger vision transformer model, having a convolutional neural network teacher is better. Maybe because that way somehow the inductive biases, which reflects in coordinates CNN's output, is transferred through backpropagation into the, I don't like to say transferred, but this whatever inductive biases like locality, translational invariance, all those biases CNNs have or convolutional filters have, it's directly communicated or it's indirectly communicated to the vision transformer when CNN is a teacher. But when vision transformer is a teacher, that possibility does not exist. So table 2, now let's see what the table 2 shows. So table 2, you have on one case data efficient image transformer, accuracy 81.8. But when you pre-train it, fine-tune it on 384 pixel images with distillation, your accuracy goes up to 83.1. Then regnet y4gf 8gf. What is this 8gf? Let's ask ChatGPT. Here, what is the 4gf, 8gf, etc. And meanwhile, let's look at the table once more. These are the models, and we compare the ImageNet performance of the student as a function of the teacher model used for distillation. So I assume these are different teachers used in the training process. Okay, 4 gigaflops. Okay, this is gigaflop. Flop is one floating point operation. Gigaflop means 4 into 10 raised to 9, right? Something like that. 10 raised to 9. 10 raised to 6 is mega. 10 raised to 9 is giga. Okay, very good. So, but my question is, what is the ImageNet performance on student as a function of teacher model used for distillation? But are we then using the same teacher model but running for more epochs? Is that what this means? Let's ask. Here, is the teacher the same always? Is the GF value increasing due to increase in the number of training epochs? I am not sure. I just want an answer for this. No, the teacher is not the same. Gigaflop does not increase because of training epochs. Let me clarify. Each row is a different regnet teacher model with different number of layers, different multipliers. Okay, so teacher architecture changes. So there are 4 different coordinate models. Does gigaflop increase because of training epochs? No. Okay, it billions of floating point. This is you cannot change a model from 4 giga to 16. Okay, yeah, of course, because it's billions of floating per image. It's not for the whole. Yeah, obviously. makes sense. I completely blanked over here. Yes. So gigaflop will not change just by increasing number of training epochs. It's calculated per image anyways. Okay, sure. My bad. But what is the architecture? I'm not understanding what's the architecture difference between each of these 4 if the teacher is different. Maybe let's ask then, what is the difference between these teacher models? Architecture size, not okay. So these are models with different sizes, and because of the size difference, the amount of time it takes to, or amount of floating point operations it takes to create to go through for one image will vary. Okay, fine. And what you can see here is the bigger the model. And how do you know it's a bigger model? Because then the floating point operation per image is higher. They have higher accuracy. 83.1, 84.2. Okay, makes sense. Okay. In all of our subsequent distillation experiments, the default teacher is regnet y with 16 giga floating point operations. So this one. Okay, fine. Makes sense. Because that has the highest accuracy. So the biggest teacher we are using, and that has 84 million parameters that we trained with the same data and same data augmentation as DEIT. So this teacher, so what these guys are doing is, they don't have a pre-trained teacher of this architecture available on the internet. So they just simply train it on the same data set. So they assume that they have a teacher available. This teacher reaches 82.9% accuracy on ImageNet. So where is that given? Here. So this is the accuracy of this particular model. Let me delete this. So this is the accuracy of only the, only the data efficient image transformer without the teacher. And these are the accuracies of teachers individually, I assume. And this column is the accuracy of the student data efficient image transformer without fine tuning, just after pre-training. And these are the accuracies after fine tuning. So after fine tuning, you have slightly better accuracy. Okay, that's fine. Now let's move on to the next page. Comparison of distillation methods. We compare, I think this is a new section. We compare the performance of different distillation strategies in table 3. Okay, we'll come to that. Hard distillation significantly outperforms soft distillation. Honestly, this was very surprising to me. I thought soft distillation was better because in soft distillation, we are giving the softmax probability scores. In hard distillation, we are just saying the argmax, whichever is the highest probability score, that index item is told to be the ground truth. So in my mind, if somebody had asked me, the whole point of teacher is not just to get the ground truth from the teacher, but also to get the softmax distribution from the teacher. So if I had not read this paper, I would have blindly said, actually, soft distillation is better. So this, for me, this is a little bit counterintuitive that hard distillation outperforms soft distillation. Even when only using a class token, hard distillation reaches 83% at resolution of 224 by 224 compared to soft distillation of 81.8%. Okay, maybe one way to justify this is, if we are doing hard distillation, whatever, let's say lack of confidence the teacher may have, we are not transferring that to the student. It's as if the teacher is confidently saying, no, this is the right answer with a great certainty. On the other hand, in soft distillation, the teacher is saying, yeah, most likely this is the right answer, but there is a small chance that these also can be the right answer. So maybe it's as if the student gets a little bit not confused. Student is not becoming as confident, something like that. I like this qualitative example to justify it, but still it's hard for me to believe that. I thought the whole point of teacher-student model in knowledge distillation was to bring not just what the teacher think is the hard correct answer, but also the teacher's softmax distribution. I thought that was very important, but here this is a bit counterintuitive for me. Let me ask ChatGPT, why is this the case? And to ask this question, I'll use whisper flow so that I can convert speech to text. This is a little bit counterintuitive for me. I would have thought that the soft labels from the teacher is the whole value which the knowledge distillation provides. So how come hard distillation gives us better accuracy compared to soft distillation? Okay, so I just use whisper flow to type. It's a nice speech to text software. You should try it. I have a paid subscription, but they have a free version also. It provides certain number of tokens per week. Soft labels are the whole magic. At first glance, DEIT's results hard distillation greater than soft distillation looks completely upside down. But there are strong and very specific reasons why soft distillation fails for vision transformer. Soft distillation assumes teacher plus student sees the same features. Soft distillation works best when the teacher and student extract similar kind of features. So teachers' logics give useful gradient information. Okay. Yeah, makes sense. If there are two convolutional neural networks, they both try to learn different features. But here we have convolution teacher trying to not teach convolution student, but convolution teacher trying to teach transformer. So features are completely different. Okay, fine. Coordinates use local receptive fields. Transformers start with global attention. Okay, that's also fine. We know that. So for the soft probabilities, so the soft probabilities from ConvNet do not align with what the transformer is able to represent in early in the training. Result KL divergence becomes noisy. Okay, I think it qualitatively kind of makes sense. Hard distillation uses one hot ground truth. I mean, one hot for the class token and teaches argmax for the distill token. So the teacher gives only one single bit of information, teacher's most confident label. This removes the shape of the teacher probability distribution. Okay, so basically what ChatGPT is saying is, if we were training convolutional neural network using another convolutional neural network teacher, maybe soft distillation would have been better. But here we are training a transformer using CNN. And because CNN and transformers look at different features, because CNNs look at local features, because filters are looking at that locality, whereas transformers have ability to pay global attention. Even if the patches are far apart, you can have very high attention weights between them. Because of that, it's better to give a confident hard distillation or hard argmax scores instead of giving the soft logits. Kind of makes sense, I would say, intuitively, but still not mathematically enough. But I guess whatever, we'll dive deeper into this when we have a chance in the future. But for now, I believe their result for sure. Our distillation strategy from section 4 further improves the performance, showing that two tokens provide complementary information useful for classification. So distillation, of course, improves the classification performance. The classifier on the two tokens is significantly better than the independent class and distillation classifiers, which by themselves already outperform the distillation baseline. So what they are saying is, classifier where both of these tokens, class token and distillation token, is considered, is better than just considering either one. So now let's look at table 3. What is table 3? Distillation experiments on ImageNet with DEIT, 300 epochs of pre-training. We report the results of our new distillation method in the last 3 rows. We separately report the performance when classifying with only one of the class or distillation embedding. So if for final classification during testing, if only class token or only distillation token are used, we report that separately. And then with a classifier taking both of them as the input. Okay, so where is both of them as the input? The last one is the both of them as input. So here class and distillation token are used for the input. And hard distillation is done using the teacher. Softmax, the ground truth label is whatever the ground truth label is. And the best performance does not result from the tiny model. It results from the baseline model fine-tuned over a data set with images 384. So they have 84.5% as the performance. Now, what does this mean? You are performing distillation. Here also you perform distillation, but you take the distillation tokens embedding. And if that is done, you reach slightly below accuracy, 84.4 after fine tuning. And if you use the embedding from class token for final testing, then you use 84.2. So distillation tokens representation seems to be slightly better than class tokens representation for final results. But if you use representation from both class and distill token, that is even better. And if you use data efficient image transformer without distillation, meaning there is no teacher, only the ground truth is there, then the 83.1, that is the accuracy at the output. If DEIT with usual distillation, what does this mean? Usual distillation means teacher is there, teacher softmax is used, but ground truth is not used. So which means what I understand here is there is no distillation token. There is only class token, but the class token is trained using teacher's softmax or soft labels. It's not trained using ground truth. In that case, you reach 83.2% accuracy. And DEIT hard distillation is, again, you don't have distillation token. This is my understanding. My understanding is it does not have distillation token. It has class token and it uses hard distillation from the teacher. So that's why the ground truth label is not there. That is how I'm understanding. Maybe I can ask ChatGPT. In the first 3 rows, is there a distillation token part of the architecture? maybe distillation token is part of the architecture. Maybe what they're doing is distillation token is there, but for the ground truth, they are not using the ground truth data, but rather they are using the output coming from the teacher in the form of either soft label or hard label. Maybe that is what these rows means. Because to call something as a data efficient image transformer, it doesn't make sense to call a vision transformer as DEIT. And when does the vision transformer become DEIT? If it has a distillation token. So I think for the first 3 rows also there is probably distillation token, but let's see. And the answer, first 3 rows there is no distillation token. Architecture is exactly same as, okay, this is what my original thought was. Let me give the full context. I am not 100% sure if ChatGPT is correct here or not. Because why should they call it as a DEIT if there is no distillation token? Doesn't make too much sense. Here is the full table. Okay, in short, the first 3 rows, there is no distillation token at all. Okay, so what I was thinking initially was correct. I mean, this is how paper reading works, right? You think something, it may be then you think it's wrong, then you understand that it's correct. So, okay, I guess it's a DEIT method where there is no distillation. Yeah, I mean, this is the symbol, this weird symbol represents the whole idea of distillation token. So maybe first 3 does not have distillation token. Okay, so the short answer or the basic takeaway from this table is you need distillation token. You need to consider while testing the output from both class token and distillation token to produce the final output. And from the teacher, don't do soft distillation, use hard distillation, and do fine tuning on the baseline model with 384 by 384 sized image. Then you will get the best accuracy. That is what this table is saying in short. Okay. This difference. Okay, now let's look at where were we? Better than, yeah, the distillation token gives slightly better result than the class token. We saw that in the table. It is also more correlated with the coordinates prediction, that we know because distillation token is trained to make predictions similar to convolutional neural networks predictions. This difference in performance is probably due to the fact that it benefits more from the inductive bias of the coordinates. Yes, distillation token is directly trying to predict what the coordinate is trying to predict as a hard label. And maybe because of this, distillation token is more attuned to whatever inductive biases are there in CNN. We give more details and an analysis in the next paragraph. The distillation token has an undeniable advantage for the initial training. Okay. Agreement with the teacher and inductive bias. As discussed above, the architecture of the teacher has an important impact. Does it inherit existing inductive bias that would facilitate the training? While we believe it difficult to formally answer the question, we analyze in table 4. Where is table 4? I think it's in this was table 3. Okay, so we are yet to see table 4. While we believe it difficult to formally answer this question, what question? Formally answer the question that whether the presence of teacher kind of allows the vision transformer to inherit inductive bias or not. That is the question. So it's difficult to formally answer it, but we analyze in table 4 and the decision agreement between the coordinate and teacher. Coordinate teacher, our image transformer DEIT learned from labels only, and our transformer DEIT with distillation. So here in table 4, they will show the agreement between 3 models: coordinate teacher, then the vision transformer DEIT vision transformer learned from the labels only, which means learned from the ground truth, and then vision transformer DEIT, which is learned from along with the distillation token. Our distill model is more correlated with coordinate than with transformer learned from scratch. Okay, as to be expected, the classifier associated with distillation embedding is closer to coordinate than the one associated with class embedding. And conversely, the one associated with class embedding is more similar to DEIT learned without distillation. So many sentences. What exactly are we saying here? If data efficient image transformer does not have a distillation token, right? And so let's say that's case number 1. Okay, so 3 cases here. One is connet, 2 is DEIT only, so DEIT without distillation token, third is DEIT with distillation token. Now this without distillation token has class token, with distillation token has class token and distill token, correct? Now what they are saying is the output of this guy is more correlated to this, and the output of this guy is more correlated to this, is what they are saying. Output of distillation token correlates more with convolution network. Output from the class token correlates more with DEIT's output, where it has no distillation token. Unsurprisingly, the joint class plus distill classifier offers a middle ground, meaning if we use both of these for classification, CLS plus distill for classification, that correlates neither with this nor with this. It's somewhere in between. The correlation is somewhere in between. It's neither perfectly correlated with ConNet's output nor with DEIT without distillation. That is what this paragraph is saying. Let's look at the table 4. Disagreement analysis between ConNet, image transformer and distillated transformers. So basically CNN, although they call it as DEIT, this is literally vision transformer, and last one is DEIT with that symbol, this symbol, whatever this is called. Disagreement between ConNet, image transformer and distillated transformers. So this is table 4. I wish they had provided this table for like a symmetric square matrix. So basically there are 6 items in the row and there are 6 items in the same 6 items in the column. And if you look at the values, all these diagonal items are 0. Basically disagreement between ground truth values and ground truth value. Disagreement between ConNet's predictions and its own predictions. So all these diagonal elements are 0, and obviously there will be symmetry. So this item will be this same value will be same as this, because this is the disagreement between ConNet and ground truth. This is also the disagreement between ground truth and ConNet. So disagreement between ConNet and ground truth is same as that between ground truth and ConNet, right? So its transpose is same as itself. But what we want to focus on is what was mentioned here in the text. In the text, they said that if you just look at CLS token for classification, the disagreement between or agreement between that and data efficient transformer without distillation token is higher, which means disagreement between this guy and this guy will be higher than between this and this. Let's see if that is the case. So CLS token is this, the one with CLS token, and disagreement between that and which item are we now looking at? We should look at the disagreement between that and just the DEIT. And what is just the DEIT? Just the DEIT is this column. So one is this item. So that is the disagreement, one item. Another item is with ConNet. And where is ConNet? ConNet is this. So if you look at the one with class token, its disagreement with the one with just class token, its disagreement with ConNet is the highest, as it should be, because the class token is like the vision transformers class token. So that token will not be really good at inheriting, like it won't get any translational invariance or any inductive biases from the CNN. So disagreement will be higher towards ConNet. On the other hand, if we look at distillation token, its disagreement towards which one should be high? Its disagreement towards ConNet should be low. Its disagreement towards just a vision transformer type of model should be high. And where is that shown? Just here. So look at these two numbers. If you use a data efficient image transformer with distillation, and if you use only the distillation token for classification, then the results you get will be similar to the results you get from the ConNet. And as you can see from the disagreement score here is low. This is ConNet, and this is distillation token for classification, and this is vision transformer, and this is distillation token for classification. So, but on the other hand, if you compare the output from your distillation token with that of just a vision transformer, disagreement is higher. And if you use classification token and distillation token, What are the disagreement values? Disagreement values are in between. So this 102, 0.102 is between 0.100 and 0.112. 0.107 is between 0.10. It's not actually between. It's comparable. That much I can say. If you use class token and distill token. But for inductive biases, if we speak only about inductive bias, just the distill token means it will be very similar to CornNet. So the dissimilarity score will be least when you compare with CornNet. If you only use classification token, its dissimilarity with compared to CornNet will be higher, 0.112. If you use both classification token and distill token and compare it with the outputs you get from CornNet, it will be somewhere in between. So 0.102 is the disagreement, which is between 0.100 and between 0.112. That is what was written. Okay. Now let's move on. Number of epochs. Increasing the number of epochs significantly improves the performance. See figure 3. Where is figure 3? Figure 3, I'm not sure if we saw. Yeah, this is figure 3. Okay, let's come back. First read and we'll come back to figure 3. With 300 epochs, our distilled DEIT is already better than DEIT baseline. But while for the latter, the performance saturates with longer schedules, our distilled network clearly benefits from a longer training time. Where do we see that? In figure 3. So this is the one with distillation and fine tuning, and its accuracy has not saturated yet. On the other hand, if you do not have a distillation token, if you simply use a teacher network for creating soft labels for your classification token, its accuracy is something like this. There is no benefit of doing further epochs. On the other hand, if you are using distillation token with fine tuning, or without fine tuning, here this one is without fine tuning, here the accuracy is showing slight improvement, whether it's a hard distillation or whether it's with distillation token, right? So that is what you see here. Whereas if you are not having the distillation token, your performance is not at all improving just by increasing the number of epochs. So distillation on ImageNet with DEIT-B, DEIT baseline performance as a function of number of epochs. We provide the performance without distillation, horizontal dotted line, as it saturates after 400 epochs. Okay. So performance without distillation saturates after 400 epochs at around 82.1% or something like that. Okay. Now, efficiency versus accuracy. We saw this in figure 1 actually. Efficiency on the x-axis, it was the speed, right? Images processed per second. Y-axis was accuracy. A comparative study with CornNets. In literature, the image classification methods are often compared as a compromise between accuracy and another criterion, such as flops. Flop is floating point operations per second, or number of parameters. Accuracy versus number of parameters, accuracy versus flops, or accuracy versus size of network. We focus on figure 1 on the trade-off between throughput, which is images processed per second, and top 1 classification accuracy. This we already saw that better than efficient net, our vision data efficient image transformer could perform. We focus on the popular state-of-the-art of efficient net CornNet, which has benefited from years of research on CornNet and was optimized by architecture search. So there was an idea called NAS, which was neural architecture search, where we don't come up with the architecture ourselves. We perform a lot of training to see which architecture provides the best result. So this efficient net was optimized by architecture search on ImageNet dataset. Our method DEIT is slightly below efficient net, which shows that we have almost closed the gap between vision transformers and CornNet when training on ImageNet. Where does it say it's slightly below? In figure 1, was the accuracy slightly below? Let's see. Maybe it was. So DEIT-B. Okay, so this is the baseline model without fine tuning. That accuracy is slightly below this guy. Yeah, this is not the exact same horizontal line, slightly below. So maybe they are referring to this point and this point, because this point is obviously after fine tuning, the accuracy is of course higher. But that fine tuning, you can't compare, right? Because this is a pre-trained model, this is pre-trained model. So you're comparing two pre-trained models, but they are essentially the same, slightly below, but almost the same. So look at the sentence that they have written. I really like this. So our method DEIT is slightly below efficient net, which shows that we have almost closed the gap between vision transformer and CNN when training with ImageNet only. This point is very important. See, vision transformer actually had their state of the art, but that was not by training on only ImageNet. For that, they trained on many other data sets. But here, if you are comparing those models which are only trained on ImageNet, this paper has truly closed the gap between transformers and CNNs. These results are a major improvement, plus 6.3% improvement on top one in a comparable setting. Comparable setting meaning 86 million parameters over previous vision transformer models on ImageNet 1K only. Furthermore, when DEIT benefits from the distillation from a relatively weaker RedNet Y to produce DEIT distilled version, it outperforms efficient net. So basically, this is the other data point. So if there is a little bit of fine tuning, in figure 1, let's go back. Yeah, so if there is a little bit of fine tuning, DEIT overcomes the efficient net. Now let's go back. I can't believe we have covered these many pages so far. It also outperforms by 1%, the top one accuracy. The vision transformer B model pre-trained on JFT 300 million at resolution 384. Yeah, so basically, if DEIT benefits from distillation, it outperforms efficient net. It also outperforms vision transformer base model, while being significantly faster to train. So vision transformer base model was 84.15% accuracy. This was 85.2% accuracy, more than 1 percentage point improvement. Table 5 reports the numerical results in more details and additional evaluations on ImageNet V2 and ImageNet Real. So these are two more other datasets other than ImageNet 1K that have a test set distinct from ImageNet validation, which reduces overfitting on validation set. Our results show that data efficient transformer base model and base model with fine tuning outperform by some margin the state of the art of trade-off between accuracy and inference time on GPU. Okay, so this table 5 must be a very big table. Yeah, so here they are showing bunch of results. I don't want to go through all of these because the summary of this result is DEIT with fine tuning, and if you compare that against rest of the models for performance versus or accuracy against efficiency, DEIT base model with fine tuning wins. So that is the essence of this table number 5. It's a very big table. You can go through it if you have the time and patience, but here it doesn't. We already know what they have said in this table through the text that we have read. So this is just this entire page number 12 is that table. So now we can move on to next page. Figure 3 we have looked at. See, we are almost close to wrapping up the paper. Transfer learning, performance on downstream tasks. Although DEIT performs very well on ImageNet, it is important to evaluate them on other datasets with transfer learning in order to measure the power of generalization of DEIT. Because it is not just enough that your model works really well on one dataset, because if your model is truly good, it should also work for other datasets after fine-tuning. So we evaluated this on transfer learning tasks by fine-tuning on the datasets in table 6, which is table 6. Maybe it's given in the next page. Yeah, table 6. So these are the data sets, the CIFAR 10, CIFAR 100, flowers data, then ImageNet, other ImageNet data sets, etc. So this is table 6. Table 7 compares data efficient image transfer learning results to those of vision transformer and state-of-the-art convolutional architecture. So table 7 compares DEIT transfer learning against that of ViT and that of CNN. Let's see table 7. Table 7, we compare transformer-based models on different transfer learning tasks with ImageNet pre-training. So after ImageNet pre-training, these are the results. And then these are all after fine-tuning, etc. Okay, and let's see the results. So first of all, if you look at EfficientNet B7, so this is one of the best models. This has a really good accuracy, but a fine-tuned DIT model on ImageNet dataset only, I think, but 384 resolution, it slightly outperforms. Then on CIFAR 10, this has 98.9, but this has better result. Here, EfficientNet has 91.7. Here it has 91.4. Here it is 98.8. This is 98.9. Then EfficientNet is 94.7. Here it is 93.7. Then here there are no results. Here it is 55.1 image number of images processed per second. Here it is 85.9. So the true competitor is CNN. That's the true competitor. And if you look at this model versus EfficientNet CNN model, the performance in terms of speed is much better for data efficient image transformer compared to CNN. That's first thing. Second thing is, if you look at the other tasks in this row, and if you compare those numbers against this row, the performance is very much comparable. That's the other thing. And what if you compare with vision transformer? Let's say vision transformer large with 32 is the patch size, I guess. Of course, this number is very small. Number of images it can process per second are high for sure. So that is good. CIFAR 97.9, CIFAR 187.1, not good. Flowers dataset 86.4. So clearly here, if you look at a clear winner, right? In my opinion, the clear winner is this model. Now, if I go back to maybe, let's say, a model where there is no fine tuning using 384 resolution images, then there is slight decrease here. So just after pre-training, it's 83.4, but CIFAR 10 is very good accuracy, comparable accuracy with any other model. Here the accuracy is slightly low for this CARS dataset. INAT dataset, anyway, there is not much to compare against. Only you can compare these against themselves. But look at the images you can process per second, much higher, right? So the clear winners are, in my opinion, the data efficient image transformer with distillation with fine tuning on higher resolution image and without fine tuning. So all these models are really good. Okay, so that is what table 7 is. So what was the text? Table 7 compares result. DIT is on par with CNN, especially the EfficientNet, which is in line with our previous conclusion. Comparison versus training from scratch. We investigate the performance when training from scratch on a small dataset without ImageNet pre-training. Okay. Training from scratch on small dataset without pre-training. We get the following results on small CIFAR 10 dataset, which is small with respect to number of images and labels. So for CNN, oh no, not CNN. This is the, I guess this is the CNN alone. If you use CNN alone, it has 98% accuracy. If you use data efficient image transformer baseline model, it has 97.5. If you use the baseline model with distillation, it has 98.5. So here also, this baseline with distillation is outperforming CNN. From this experiment, we try to get as close to as possible to the ImageNet pre-training counterpart, meaning we consider longer training schedules. Okay. Up to 7,200 epochs. Wow, amazing. Which correspond to 300 ImageNet epochs. Okay, maybe makes sense because now this is a smaller data set. So 300 epochs on ImageNet data is comparable to 7,200 epochs on this CIFAR 10 dataset, so that the network has been fed a comparable number of images in total. Okay. Second, we rescale the images to 224 by 224 to ensure that we have the same augmentation. Okay. The results are not as good as with the ImageNet pre-training, 98.5 versus 99.1. Where is that? Here. So 98.5 versus 99.1 when we pre-trained with ImageNet. And where is that 99.1? This is ImageNet and this is DEIT baseline. And where is CIFAR 10? This one. This is the CIFAR 10. So this this one. So this model is pre-trained on ImageNet. So on that, it's 99.1, which is expected since the network has seen a much lower diversity. Completely makes sense. However, they show that it is possible to learn a reasonable transformer on CIFAR10 only. Basically, CIFAR10 is a very small data set, and you can teach a vision transformer architecture through knowledge distillation, where knowledge distillation happens from a CNN like this one, but the data set is a much smaller data set like CIFAR10. Let me actually compare CIFAR10 versus ImageNet 1K dataset size difference. So CIFAR10 it's a 10 class classification, 50,000 images in training, 10,000 in testing, 32 by 32. ImageNet 1K has 1,000 classes, of course, 1.2 million images and 50,000 for validation. So obviously this is what? 20x bigger, right? At least minimum 20x bigger, 25x actually to be exact. So that is the size difference. Okay, fine. Now let's move on. Training details and ablation studies. In this section, we discussed DeiT training strategy to learn vision transformers in a data efficient manner. We built upon PyTorch and the TIM library. We provide hyperparameters as well as an ablation study in which we analyze the impact of each choice. Initialization and hyperparameters. Transformers are relatively sensitive to initialization. After testing several options in preliminary experiments, let's read this. TIM implementation already included a training procedure that improved accuracy of vision transformer base from 77.9 to 79.3 and trained on ImageNet 1K with 8 V100 GPU. Okay. After testing several options in preliminary experiments, some of them not converging, we followed the recommendation of Hanin and Roenick to initialize the weights with a truncated normal distribution. Okay, basically, do not go with random weight initialization. Go with some truncated normal distribution, although I don't know what it means. Table 9 indicates the hyperparameters that we use by default at training time for all of our experiments unless stated otherwise. For distillation, we follow the recommendation from Shaw et al. To select parameters tau and lambda. Tau is the temperature, lambda is the scaling factor for each of the cross entropy loss and the KL divergence score. We take t equal to 3 and lambda equal to 0.1. So 0.1 means what? Lambda cross entropy loss has 1 minus lambda or lambda. Let me check in this formula. So cross entropy loss had 1 minus lambda. So 90% of the loss is attributed to cross entropy loss. 10% is attributed to the KL divergence loss. Okay, that is fine. We are pretty much close to wrapping up the paper at this point. Okay, and this table is about their hyperparameter. I don't want to go through this. You can go through this comfortably later. It's just what for their experiments, what kind of hyperparameters were the best which resulted from their ablation studies. Data augmentation. Compared to models that integrate more priors such as convolution, transformers require large amount of data. We know that. Thus, in order to train with data sets of same size, we rely on extensive data augmentation. So augmentation means random cropping, random flipping, changing maybe introducing graininess, adding blur. Basically augmentation techniques which produces new data points from the existing data points. We evaluate different types of strong data augmentation with the objective to reach a data efficient training regime. So they use auto augment. We don't have to go into exact details of the augmentation techniques unless we are interested in implementing this. Random augmentation, random erasing, and improve the results. For the latter two, we use TIM customizations, and after ablation, we choose rand augment instead of auto augment. So I guess for rand augment, there should be a tick somewhere here. Rand augment, auto augment. Yeah, so they have a tick against auto augment for data augmentation. All right. And overall, our experiments confirm that transformers require strong data augmentation. Almost all data augmentation methods that we evaluate prove to be useful. One exception is dropout, which we exclude from our training procedure. So perhaps dropout was not useful for them. So here you can see that In Vision Transformer, they had a dropout of 0.1, but here they did not have a dropout. So that is a difference. So here, this is a comparison between hyperparameters and what all things were used, where you compare Vision Transformer base model and data efficient image transformer base model. So batch size, epochs 300, batch size 4096, 1024, optimizer Adam W, same, learning rate 0.003. So here it's a function of batch size, cosine learning decay rate, weight decay 0.3.05, warm up epochs, label smoothing. Yeah, obviously Vision Transformer did not have any label smoothing. Dropout, gradient clipping, repeated augmentation, random augmentation. Yeah, Vision Transformer did not have any of this. This was not there in Vision Transformer. Gradient clip. Let's just ask what is grad clip. What is grad clip here? You limit the size of gradients during backpropagation to prevent them from becoming too large and destabilizing the training. All right. When we implemented the Vision Transformer from scratch, I don't remember us implementing this anywhere explicitly. We did not do this, but I guess in the original paper, they might have done it. Okay. Regularization and optimizers. We have considered different optimizer. Okay, so this paragraph is just an explanation of what this table 9 is, I guess. They must have referred to this table 9 somewhere in this paragraph. But learning rate is learning rate by 512 multiplied by batch size. But these are just specific details of what they did, not conceptual. Exponential moving average. We evaluate exponential moving average for our network obtained after training. Fine-tuning at different resolution. So instead of just 384 resolution, they might have tried fine-tuning at other resolutions. So 384 by 384, 320 by 320, 224 by 224, 160 by 160. So 160 by 160 means the model will be the worst. I can imagine that, but it will have very good speed. So image throughput is very high, but ImageNet accuracy is very low, 79%. This has the highest accuracy, 83.1, but it's the slowest in terms of image throughput. Completely makes sense. We also interpolate the position embeddings. In principle, any classical image scaling technique like bilinear interpolation could be used. This is to create positional embeddings if you are using lower resolution or higher resolution images. They might have mentioned it here. But we keep the training time data augmentation contrary to the dampened data augmentation. Okay. I think these parts are fine. And one thing is Adam W. They say Adam W with STD or no STD. In Adam, we know that we have adaptive moment and adaptive learning rate. Difference between Adam W and Adam. So in Adam, we know that there is adaptive moment and learning rate scaling, but Adam with decoupled weight decay. Better optimization, Adam with L2 regularization. Okay, this is not something that we need to go into right now. It looks like a straightforward thing. We know what Adam is, but I guess this is more about weight decay rather than about implementation of Adam itself. By default, and similar to Vision Transformer, we train data efficient image transformer at a resolution of 224 and we fine tune at a resolution of 384. So this we know. We detail how to do this interpolation in section 3. However, in order to measure the influence of the resolution, we have fine tuned DeiT at 3 different resolutions in table 10. In fact, 4 different, right? Okay, apart from this, 3 other resolutions. 160 by 160 is smaller than 224 by 224, so it should be worse. Training time. A typical training time, 300 epochs takes 37 hours with 2 nodes or 53 hours with single node. As a comparison point, a similar training with this RegNet 16 gigaflops, 84 million parameter is 20% slower. DEIT S and Tiny are trained in less than 3 days on 4 GPU. Then optionally, we fine-tune the model at a higher resolution. This takes 20 hours on a single node 8 GPU to produce fixed DEIT B model at resolution 384 by 384, which corresponds to 25 epochs. Not having to rely on batch norm allows one to reduce the batch size without impacting performance, which makes it easier to train larger models. Oh, really? Not having to rely on batch norm allows one to reduce the batch size. Oh, I was not so sure why batch normalization is problematic when why batch size changing is problematic when there is batch normalization. Why is it an issue to change the batch size if batch normalization is present? This is exactly why DEIT avoids batch normalization and instead uses layer norm. Because in layer norm, you are normalizing each dimension of every single input. In batch normalization, it's done batch wise. Changing the batch size is a problem when batch norm is present because batch norm computes statistics per batch. Small batch, noisy estimates, large batch, stable estimates, changing batch size, changes statistics. Of course, we know this, but is there any other reason? That's what I want to know. Layer norm, we know this is also fine. Layer norm is simply you normalize the mean and standard deviation, mean equal to 0, standard deviation close to 1. For, let's say there are 784 dimensions for a given vector. You normalize every single dimension. Okay, so I guess, but this I already knew. Whether for small batch you will have some set of estimate. For larger batch, some other estimate. So maybe if you play with the batch size randomly, your results may be different. But I knew that already. I was not so sure. Because of this, you will eliminate batch normalization altogether from your training. That is something that was surprising here. It's a little bit surprising. I need to read about this a little bit more. Note that since we use repeated augmentation with 3 repetitions, we only see 1/3 of images during a single epoch. Okay, that makes sense. If you have 3 augmentations for each epoch, or note that since we use repeated augmentation with 3 repetition, we see only 1/3 of images during a single epoch. Oh, is it? Why is that? I thought in one epoch you go through the entire data set, right? Isn't it the case that in one epoch you go through the entire data set? So how come for one epoch you're only seeing 1/3 of your images here? Even in the presence of augmentation, I thought the whole augmented data set becomes your training data, and in one epoch you go through all of that. You divide those into batches and you go through all the batches in one epoch. Normally one epoch equal to see every image once. Repeated augmentation means but DEIT breaks this definition on purpose because they use a special trick called repeated augmentation, and they use it very heavily, 3 repeats. This means that changes what an epoch means. Repeated augmentation with n repetition means each image is repeated n times within a single epoch, each time with a different augmentation. Okay. For RA equal to 3, each image is augmented in 3 different ways. The data loader emits 3x more samples, but the dataset length remains the same in terms of epoch definition. Oh, I see. So if every single image is producing 3x more images, when you are sampling a batch, you are very likely to have augmented copies of the same image in the same batch, which usually will not happen if you are not performing augmentation. So because of this, since you are performing 3 times 3 augmentation steps, on an average, you are only looking at 1/3 of 1/3 unique images per batch. I think that's the way I understand this. In any case, we are at the end of the paper. Conclusion: in this paper, we have introduced DEIT, which are image transformers that do not require very large amount of data to be trained. Okay, here actually they are providing a footer. Formally, it means we have 100 epochs, but each is 3x longer because of the repeated augmentation. We prefer to refer to this as 300 epochs in order to have direct comparison on the effective training time with and without repeated augmentation. Okay. So if they have 100 epoch, essentially it's like having 300 epochs, because each data point is going through 3 augmentations. Okay, basically in this paper, they introduced DEIT, which are image transformers that do not require very large amount of data to be trained, thanks to improved training and in particular novel distillation procedure using distillation token, of course. CNNs have optimized both in terms of architecture and optimization almost during the decade from 2012 to 2020 plus. Both in terms of architecture, including through extensive architecture search, like this is what the neural architecture search I was talking about earlier, that is prone to overfitting, as it is the case for the instance of efficient nets. For DEIT, we have started the existing data augmentation and regularization strategies pre-existing for convnets, not introducing any significant architectural beyond our novel distillation token. Therefore, it is likely that research on data augmentation, more adapted or learned for transformers, will bring further gains. So data augmentation or any other adaptations currently they are using are already there for convolutions, CNNs. But if there are data augmentations that are more better for transformers, such changes can actually make their model even better. That's what they're saying. Therefore, considering our results where the image transformers are on par with convnets already, we believe that they will rapidly become a method of choice, considering their lower memory footprint for a given accuracy. So for getting a given accuracy, actually transformers, at least data efficient image transformers, have better or lower memory footprint. So that is the last sentence. So with that, the paper comes to a conclusion, and that's pretty much it. I think now it's just the references. Last 2-3 pages are references. They don't have an last supplementary section or appendix section. So that's it. We come to the end of the paper. So as I promised at the start of this video recording, this paper was relatively easy. The only thing is I could not manage to do it in just one sitting. I had to take breaks because again, going through a paper is a little bit tiring. But we have officially, entirely finished this data efficient image transformer paper. I hope you enjoyed going through it as much as I did. But of course, it's tiring. I am very tired right now. I'm mentally exhausted, but I also feel very happy to have gone through the paper end to end in detail. And I hope you are also feeling the same. I hope you are feeling as tired as I am, and as happy also. So this is like, how do you compare this against, like, let's say going and taking weights in the gym? It's not easy to do that, but you get a lot of happiness afterwards. You will get tired, but afterwards you will be happy. So think of this as like a mental exercise. But I hope you are following this. I hope you are liking it, and I really hope this habit you are cultivating, habit of reading papers. I'll be taking up more papers in this series, more interesting papers, more seminal papers, and you will have a really good experience if you walk this path along with me. So I hope to see you again in another lecture. Take care until then. Bye.